Welcome to the channel. Thanks for joining us, your one-stop for everything AI. If this is your first time, please consider subscribing and ringing that all notifications bell. We are very interested in your feedback. Go ahead and share your thoughts in the comments. The realm of robotics is on the cusp of a seismic shift, with ripples of innovation disrupting this landscape in ways never imagined. At the epicenter of this impending revolution is the Unitree H1, a trailblazing quadruped robot that dismantles established notions about robotic design, mobility, and versatility. The Unitree H1 represents an inflection point where biomimicry, software, and forward-thinking engineering converge to create machines that move with organic dynamism. By taking inspiration from mammal and animal morphology, the Unitree H1 gains bipedal mobility that unlocks unprecedented agility and adaptability. This concept of creating robots that move like life forms rather than rigid mechanical constructs signals a new generation of nimble, dynamic machines. As we explore the genesis of the Unitree H1, we discover how a fusion of carbon fiber limbs, high-powered actuators, and sensor suites allows it to traverse the world with cat-like grace. We uncover how deep reinforcement learning and neural networks give it the ability to navigate any environment by learning from experience. And we glimpse into a future where intuitive control, environmental awareness, and semi-autonomy enable smoother human-robot collaboration. The Unitree H1 sits at the bleeding edge, showcasing innovations that will drive robotics advancements for years. This multidimensional marvel is more than just a flashy creation. It's a transformative technology that foreshadows how robots will soon step out of the pages of science fiction into the real world. The Unitree H1 beckons us into a landscape abundant with possibilities. The emergence of the Unitree H1 robot has ignited a seismic shift in the landscape of robotics, introducing a trailblazing creation where unbridled innovation converges with biomimetic brilliance. This dexterous tech marvel represents a new epoch, an era defined by machines that can mimic and exceed the feats displayed in the natural world. As we explore the genesis of the Unitree H1, we uncover an intricate tapestry of ingenious design, dynamic algorithms, and human artistry that empowers this robot to push the frontiers of capability and reimagine what the future beholds. The journey that led to the Unitree H1's genesis is one of relentless curiosity to uncover new realms of possibility. For years, sci-fi narratives tantalized our imagination with visions of agile robots. The Unitree H1 shattered these limitations with its four-legged mammalian form that unlocked unheralded potential. This ingenious recreation of quadrupedal movement marked a new chapter in robotics, one guided by biomimicry instead of pure mechanics. But the road that led to this breakthrough was paved with small steps. In the past, robotics researchers experimented with quadruped designs, drawing inspiration from the effortless agility of animals. Models like Big Dog, Cheetah, and Wildcat offered glimpses into this promising new paradigm, but were held back by limitations in their control systems, power, and versatility. The Unitree H1 took this foundation and added a secret sauce, an interplay of form and algorithms that elevated it beyond being just a mechanical facsimile of life. Its 12 high-powered actuators, custom limb design, and sensor-laden nervous system gave it lifelike dynamism. But the real magic lay in the neural networks powering its motion. Machine learning models honed over thousands of trials until the robot could navigate the world with animal-like intuition. This perfect storm of engineering and computation marked the dawn of a robotics revolution. As the Unitree H1 stepped out into the world, it heralded an age where machines could transcend their origins as rigid, single-purpose automatons. Its seamless gait as it walked, ran, and jumped was a declaration that the future of robotics would be guided by an ethos of biomimicry and fluid versatility. Like life itself, this robot showcased how elegance can emerge from complexity, and how with enough insight, we can replicate nature's genius in an artificial substrate. The Unitree H1's unprecedented capabilities are enabled by an intricate fusion of meticulous mechanical engineering and bleeding-edge algorithms. Peeling back its exterior reveals a marvel of coordinated design that brings an unlikely union of rigid actuators, sleek carbon fiber, and intricate sensor systems to life. At the core of this dexterous dynamo is a mechanical anatomy designed from the ground up for agility and efficiency. Its limbs, crafted from carbon fiber, move with precision and power, driven by 12 high-torque actuators, sealed within a sleek exterior while drawing minimum current, granting it cat-like acceleration. But the Unitree H1 is more than just motors and metal. Its nervous system comprises a multitude of sensors, ainews, cameras, lidars, that endow it with animal-like reflexes and situational awareness. Each foot is studded with pressure sensors that provide touch feedback, enabling it to dynamically adapt to any terrain. So unlike industrial robots bolted to the ground, It can traverse the unpredictable real world with lifelike flexibility. Synchronizing these diverse components is the magic of algorithms, lines of code that mimic the role of nature's neural pathways. Proprioceptive sensors and complex state estimation algorithms give it a sense of balance and body awareness that guides its every step and leap. And like a gymnast, it optimizes momentum and energy in real time by drawing on a wealth of collected data and simulations. What emerges from this symphony of mechanics and computation is a machine that almost transcends its artificial origins. As it moves with uncanny organic fluidity, the Unitree H1 represents a new breed of robots, ones that borrow principles from nature to achieve what rigid mechanical machines cannot. It epitomizes a future where humans and algorithms work in unison to recreate life's genius within synthetic substrates. The Unitree H1's crowning achievement is enabling robots to walk, run, and leap with unprecedented organic agility. This quantum leap in mobility is enabled by its four-legged mammalian form factor, a biomimetic design that unlocks capabilities beyond the reach of wheels and treads. Confining robots to rolling bases worked well in controlled environments. But these traditional designs falter outside structured factory floors and roads, lacking the dexterity to handle stairs, uneven terrain, or obstacles. The Unitree H1 breaks free of these shackles by adopting the efficient, four-limbed anatomy of animals specialized for mobility. This strategic recreation of quadrupedal movement confers extraordinary advantages. The addition of multiple contact points with the ground enhances stability and balance. Powerful actuators in each limb allow rapid changes of direction and orientation to swiftly adapt to dynamic environments. And by seamlessly varying its gait, it achieves energy efficiency, whether moving at a gentle trot or rapid gallop. But the Unitree H1 showcases how quadrupedal robots can achieve feats beyond just efficient mobility. The Unitree H1's biomimetic form lays the foundation for its groundbreaking mobility. The strategic placement of its limbs enables advanced maneuvers like jumping gaps, climbing steps, and even performing backflips. And by coordinating the interplay of sensors, motors, and algorithms, it can walk delicately across uneven terrain and recover its balance after disturbances, feats once thought impossible for any machine. As we witness the Unitree H1 traverse the world with such organic dynamism, it becomes evident that evolution settled on the optimal anatomy for mobility. By replicating quadrupedal movement in silicon and steel, the Unitree H1 represents robots transcending the constraints of wheels to achieve lifelike agility. This quantum leap in form and function signals an inflection point where technology moves closer to mimicking biology's genius. But crossing the uncanny valley into lifelike dynamic motion required unlocking the power of algorithms, neural networks, and massive data sets. This fusion of engineering and deep learning sparked a revolution, enabling robots like the Unitree H1 to coordinate their limbs with uncanny organic fluidity. In contrast to industrial robots that precisely replay pre-programmed motions, the Unitree H1 leverages model-based and model-free algorithms to move with remarkable adaptability. Instead of having scripted gaits and transitions, it uses learning-enabled control to optimally vary its stride, speed, and posture based on terrain. Myriad sensors provide real-time feedback to help it dynamically regulate its balance and energy efficiency when walking, running, or leaping over obstacles. This dynamic motion is enabled by generative neural network models trained with deep reinforcement learning. By attempting millions of simulated walks, jumps, and recoveries, the Unitree H1 learned to intuit appropriate responses to navigate the world. Just like animals acquire innate reflexes through experience, it developed an intuition for movement by learning from virtual experience. The Unitree H1 showcases technologies once confined to computer graphics and video games now spilling over into the real world. The confluence of cheap sensors, high-density actuators, and neural networks enabled machines to mimic the fluidity and adaptability of living organisms. As robots continue to gain mobility and awareness, their motions will only grow more dynamic and responsive through learning. The era of pre-programmed robotic motions is coming to an end, replaced by algorithms that mimic life's improvisational genius. Interacting with the Unitree H1 offers a glimpse into a future where robots respond intuitively to human guidance and environmental cues. Moving beyond rigid scripting, it incorporates AI and sensing capabilities that enable more natural forms of real-time control and collaboration. A key innovation that enhances this intuitive interaction is the incorporation of semantic labels and responsiveness modulation. Instead of controlling the Unitree H1 through raw joint and actuator inputs, users can guide it via high-level labels like walk, crouch, or jump. Based on training, it intelligently interprets these semantic commands to translate them into robust execution. This is augmented by real-time modulation of responsiveness and precision based on the task and environment. For risky maneuvers, responsiveness is tuned down to enhance safety. In cluttered environments, motion gains finer precision at the cost of speed. Such context-aware adaptation enables smoother collaboration and reduces the control burden on human operators. Looking ahead, robots like the Unitree H1 will gain even more enhanced intuition through imitation learning and virtual reality-based teleoperation. By observing and learning from human motions, they can build models that map natural body language into appropriate responses, and interfaces like virtual reality and augmented reality can close the control loop, allowing seamless high-bandwidth human supervision during complex tasks. As the Unitree H1 demonstrates, the future of robot control will be guided by AI and embodiment, not rigid programming. This grants robots the versatility to adapt in unstructured environments and work in fluid symbiosis with humans. The era of robotic intuition is dawning. The Unitree H1 represents an important milestone in the march toward enhanced robot autonomy. While not fully self-guided, it incorporates critical capabilities like environmental sensing, situational awareness, and reflexes that reduce the need for constant human intervention. This hints at a future of capable and helpful robotic partners that can operate semi-independently in human spaces. Onboard sensing equips the Unitree H1 with an elementary awareness of its surroundings. Depth cameras allow it to detect obstacles, cliff edges, and surfaces while also creating spatial maps to localize itself. LiDARs and ainews enable it to build 3D point clouds of its environment, providing situational awareness regardless of lighting conditions. These sensors feed perception algorithms that give it reflexes to avoid collisions and navigate safely. Building on this sensing foundation are autonomy elements like global and local motion planning algorithms. By combining pre-mapped areas with dynamic perception, the Unitree H1 can chart optimal paths to target destinations while avoiding unforeseen obstacles. More local, reflex-based micromotion algorithms help it safely adjust individual steps and body positions when traversing challenging terrain. While still requiring human oversight for complex cognitive tasks, these building blocks equip the Unitree H1 to take over repetitive mobility and navigation tasks. This assists users while also reducing accidents arising from fatigue and human error. The Unitree H1 showcases quadrupedal robots' unprecedented mobility, but fulfilling their potential requires designing environments where they can operate safely and effectively alongside humans. This entails architectural modifications and virtual augmentations that embrace robot capabilities while avoiding accidents. Navigation mesh overlays can guide quadruped robots through environments optimized for their unique mobility. Mapping areas with data on stair dimensions, door widths, hallway clearance, and flooring traction facilitates safer robot operation. QR matrices and RFID tags scattered through space provide positional feedback for navigation algorithms. Augmented environments also enable natural human-robot communication. Spatial grids projecting from cameras can signal restricted areas while also triggering reflexive motions like slowing or stopping. Voice-based interfaces allow humans to verbally guide robots. Smart environments avoid collisions by monitoring human and robot movement via sensors while giving robots reflexes to react. More capable onboard perception will reduce reliance on environmental augmentation. But thoughtfully designed spaces that embrace robot capabilities will remain crucial. The Unitree H1 showcases the immense potential of highly dynamic quadruped robots. But fulfilling this potential hinges on architecting environments where humans and robots can coexist safely and harmoniously. As robots like the Unitree H1 operate with increasing autonomy, ensuring safe and fail-safe operation emerges as a design imperative. This involves both fail-safes to prevent accidents as well as compliance and impact reduction to enhance safety when unforeseen contact occurs. At the hardware level, advanced pressure and proximity sensors give the Unitree H1 heightened tactile awareness and reflexes to avoid collisions, react to contact, and regulate impact forces. Software-based reflex architectures that leverage neural network models provide sophisticated reflexes and reactive control even in novel scenarios. Inbuilt compliance actuators and linkages reduce forces during unintended contact, much like natural muscle and tendon compliance. Moving beyond hardware and low-level control, higher-level fail-safes are crucial. Runtime verification algorithms constantly check software logic and sensor data against safety models, triggering shutdown if critical deviations occur. High-level oversight by humans provides common-sense guidance and damage control. And wireless remote overrides allow immediately halting the robot or downshifting to minimal risk actions. Adaptable and capable future robots will balance independence with human oversight. Just like limits we place on autonomous vehicles, intelligent policy frameworks will govern where and how autonomous quadrupeds operate based on environmental risk and benefit. With prudent design and use, robots like the Unitree H1 will usher in an era where machines become our useful and trustworthy partners. The Unitree H1 heralds a future where agile robot partners assist and empower us in work and life. As quadruped robots grow more versatile and autonomous, their potential applications are limited only by imagination. They will take on dull, dirty, and dangerous tasks while also augmenting human creativity and productivity. Search and rescue represents an early application where agile robots can assist in disaster response, exploring rubble and collapsed buildings too hazardous for human responders. Construction and maintenance tasks in challenging terrain and heights will be safer and more efficient with robotic helpers that work alongside human crews. Robots can undertake environmental monitoring, precision agriculture, and inspection in remote and hazardous areas. But applications extend far beyond just replacing human labor. Robots like the Unitree H1 will work in concert with human creativity, taking on roles in interactive live performances, theme park experiences, and multimedia projects. Children and the elderly will benefit from capable and safe robot companions, and in settings ranging from hospitals to homes, they will take on crucial caregiving duties while empowering human care providers. As the Unitree H1 demonstrates, we are at the cusp of a robotics revolution powered by biomimicry and enhanced mobility. Quadruped partners will soon become integral in our lives, ushering in an age where machines help and empower us as we help them realize their potential for good. The Unitree H1 serves as a versatile platform to push the boundaries of robotics research. Its powerful sensing, actuation, and computation capabilities enable exploring innovative ideas in design, control, autonomy, and human-robot collaboration. It also accelerates research by serving as a reusable testbed for algorithms and strategies that can be transferred to specialized future robots. Areas like gate optimization and terrain adaptation benefit from testing novel gaits and walking strategies aided by the Unitree H1's speed and dynamism, and its physical robustness and safety allow rapidly evaluating new strategies in proprioception, contact recovery, and resilient operation. New sensors and tag-based environments facilitate research in mapping, localization, and visually impaired navigation. By open sourcing much of its hardware and software, Unitree enables researchers to build on its advances. Adding new sensors helps test innovative state estimation and perception approaches. Custom neural network and reinforcement learning models can be validated through real-world trials. And programmable onboard computing enables rapid iteration of research algorithms and control architectures. The Unitree H1 is a stepping stone to specialized robots like rapid first responders, dexterous humanoid helpers, and intervention robots that assist the elderly. Research and data accumulated during its development and operation will accelerate future real-world robot deployments. If guided prudently by norms of transparency, safety, and social benefit, disruptive innovations like the Unitree H1 can uplift humanity. But this requires eschewing fear and hype for nuanced, evidence-based policies that welcome benefits while mitigating harms. A key guiding principle should be using regulations and oversight to build public trust, not just limiting functionality. Spaces for public dialogue around balancing risks and benefits will ground policies in societal needs. Channels for user feedback will continuously improve design and applications, and cross-industry codes of ethics and safety will institutionalize responsibility. Through cooperation, the horizons opened by the Unitree H1 can be made accessible to all. As we conclude this in-depth exploration, the Unitree H1 cements its status as an innovator in the robotics landscape. By mimicking mammalian morphology and motion, it empowers robots to achieve unprecedented mobility, dynamism, and versatility. Its fusion of elegant design, novel sensing, and deep learning unlocks capabilities that seemed unattainable just years ago. This robot reminds us that with insight, creativity, and purpose, we can mimic nature's genius to build tools that amplify our humanity rather than diminish it. The Unitree H1 gives us a glimpse into a future where robots become adaptable collaborators and partners, enriching life and unlocking new realms of possibility. Thank you for watching. That is a wrap. Until next time, stay curious, stay passionate, and most importantly, stay awesome. This is Make Money AI signing off. Don't forget to click the notifications bell so you never miss out on the newest updates in the world of AI. Remember, every like, comment, and share brings us closer together as a community.